Now, in the correlated sampling, the first rule is the number of replications under both system designs must be the same. So we will have m number of replications. M for the first system design and M for the second system design. And within the respective replications of the alternative system designs, we are always going to use the same random number streams or random number sequences. For example, in the first replication of the first system, if I use a random number sequence, I am going to use the exact same sequence in the first replication of the second system design, so that the first replications are going to be performed under the same artificial history, under this exact same scenario. The same customers, the same arrival times, the same service times for each customer, but instead of having 2 cashiers, we are going to have 3 cashiers. We are basically asking this question: what happens if I choose to have 3 cashiers if the exact same things happen? Therefore, I use the same random number sequences in the respective replications of alternative system designs. And again, the correlated sampling rule says that if you want to get reliable results, the number of replications should be at least 6 again. This is the golden rule, my friends. If you run a simulation with replications, and actually in terminating simulations, a replication is almost a requirement. If you run a simulation with replications, always have at least 6 replications, it says. Now, the theoretical variance that I obtain from the first system designs, sigma 1 square over m, and the theoretical variance of the second system will also be sigma square 2 over m. So the number of replications are the same. Now, here's the thing, my friends. Since we use the same random number sequences in each replication, it is possible that the results of the replications under alternative system designs to be correlated with each other. Therefore, the average across replications for the first system design and the second system design may have a correlation as well. Therefore, this covariance will not be 0 this time. And we can say that variance of the difference of the replication averages is going to be equal to variance of the theoretical average of the first system design plus the variance of the theoretical average of the second system design, which are respectively sigma 1 square over m and sigma 2 square over m, minus 2 times the covariance. And you know the covariance is calculated as what? The correlation multiplied with the theoretical standard deviation of the first random variable and the theoretical standard deviation of the second random variable. Now, you need to refresh your knowledge about the covariance from your probability theory course. So what is the covariance? The covariance between 2 random variables, x and y, my friends, is equal to the correlation between these 2 random variables times the square root of the variance of the first random variable and then the variance of the second random variable. Okay? So in that case, we can write this like this. Rho xy is the correlation among x and y times the square root of the variance of x and variance of y. If we say that variance of x is equal to sigma x square and the variance of y is equal to sigma y square, let's just say here we write sigma x and sigma y. And that is exactly what we are doing here. We are replacing the covariance here as the correlation between the first system and the second system times the square root of the first system's variance, which is sigma 1 over square root of m. And the second system is sigma 2 over square root of m. And when you multiply the square root of m's, you also get another m here. So this is exactly what we have done. And you see the variance obtained with a common random numbers methodology or correlated sampling will be the variance of the independent sampling, because in the independent sampling, the covariance is 0 minus 2 times the correlation among the estimates and the standard deviations of the estimates. So this is the difference. Now, you know, the standard deviations are always positive, right? So sigma 1, sigma 2 are always positive. And number of replications is also positive. Now, if the correlation between the first system result and the second system result is also positive, the variance obtained with the correlated sampling is going to be less than the variance obtained with independent sampling. Therefore, that result is going to be more reliable. But the condition for that is to have a positive correlation. You know, there may be negative correlations as well. If the results of the two systems are positively correlated, and usually they are, for example, when you get a larger interarrival time, then the expected Q times are going to be less, right? If the interarrival times are larger, then the Q times are going to be less. And so you see the results are going to be the same even if you have 2 cashiers or 3 cashiers. So the Q times are going to be reduced if the interarrival times are larger. So whenever you make a change in the random number sequences, both systems are going to experience the same type of difference. Same type of difference. Because even if you change the decision variable, the effects of the random number sequences are going to be usually the same. Therefore, we always observe a positive correlation in the changes made in the random number sequences in the system performance metrics. Therefore, when you use the common random numbers procedure, the variance of the comparison is going to be further reduced and we are going to get more reliable results. Now, we have learned that the variance of the correlated sampling or the common random numbers procedure, remember now CRN means common random numbers, which indicates that you are using the same random number sequence in the respective replications of alternative system designs. In that case, the variance is going to be less than the variance that you obtain in the independent sampling if the correlation between the replication averages is positive. Okay, now very less frequently, so almost never, but sometimes it happens that even though the random number sequences are the same, within replication averages may not be positively correlated, may be negatively correlated, but we need to be careful about this situation. I am going to explain when rho 1, 2 can be negative. We do not usually observe that situation in practice, but I'm going to explain when we can observe something like this. In that case, the variance of the common random numbers methodology is in fact going to be greater. So if rho here is negative, then the variance is going to be more than the variance of the independent sampling, and the results are going to be less reliable in that case. But if the correlation is positive, the confidence interval will be narrower with the lower variance, and the results will be more reliable. So how do we develop the framework of the correlated sampling then? Let's just say we again have two systems. This time we run M replications for both systems, and first replications are going to use the same common random number sequence. The second replications under the alternative system designs are using the same common random sequences, so on and so forth. So because of that reason, we have the same number of replications. Now we have the sample mean obtained from the replications of the first system and the sample mean obtained from the second system. And we also have the sample variances here. However, because we know that two samples are correlated, just like we have done in the statistics course, if you have two samples which are correlated in two sample t-test, you do not apply a t-test across the sample means. In fact, you subtract the replication averages from each other and calculate the differences as a sample. So you subtract a second system's first replication average from the first system's first replication average, and you take this as the difference between the systems in the first replication. And you subtract y22 from y21, and you calculate the difference between the two systems in the second replication, so on and so forth. Then you calculate the sample mean of this d bar, and actually this d bar, the sample mean here, is going to be the difference between these two sample means. So either you calculate the sample mean of these d1, d2, d3 values, or you can simply subtract the sample mean of the second system from the sample mean of the first system. you are going to get the same result. However, unfortunately, the sample variance of the differences here is not going to be equal to the sum of the sample variances here. Be careful. This is a very harmful, dangerous mistake that you should not do. Now, we can take the difference of the sample mean, and this is just going to be the same as the average of the differences. However, for the sample variance of the differences, you are supposed to calculate the sample variance of the differences from scratch. It is impossible for you to calculate the sample variance for the differences by using the sample variance across replications. Why it is impossible? Why? Because you do not know the correlation. You do not know the correlation. Actually, you can use the sample variance of the first system and the sample variance of the second system here, but you wouldn't be able to calculate the covariance because you do not know the correlation. Therefore, instead of calculating the correlation, actually you can calculate the correlation by using the correlation between these two, but instead of doing that, why shouldn't we use a simpler approach? Just take the differences between these two samples and calculate the sample variance of these differences. That's it. Now, we are going to apply this time a one sample t-test, not two sample t-test, and we are going to apply this one sample t-test over the sample mean of the differences and the sample variance of the differences. So we are just going to use the third row. If the question tells you that the simulations are performed by common random numbers, this is the framework that you need to apply. You need to calculate this difference row with the sample mean of the differences and the sample variance of the differences. And then you will say that when you develop a confidence interval for the expected value of the differences, if that confidence interval is in the negative region, you will say that the theta 1 is going to be less than theta 2 in that case, and system 1 is better. I mean, please be careful. We are giving our examples in the expected Q waiting times. Therefore, if the value is less, then it is better. But if the performance metric is, for example, something related to money, then if theta 1 is less than theta 2, we say that theta 2 is better. Okay, be careful. If the confidence intervals that you obtain for the expected difference is in the positive region, in that case, theta 1 is going to be greater than theta 2. Since theta values are indicating expected Q waiting times, then we say that the system 2 is better. But if the confidence interval that you develop for the differences contains 0 in it, so which means the confidence interval is partially in the positive, partially in the negative region, then the comparison is going to be inconclusive. Now, we are going to develop the confidence interval for the difference between the alternative system designs as the sample mean for the differences in the last row plus minus the t quantile for new degrees of freedom. Nu is basically equal to number of replications minus 1 because we have a sample of m observations here, and the degrees of freedom always equals to 1 less than the number of observations. And the standard deviation of the differences is calculated through the sample variance across replications, and that is going to be 1 over m minus 1 squared sum of the deviations of the differences from the overall mean of the differences. And you need to divide this standard deviation to the square root of m to calculate the standard error, and this is your confidence interval. Let's practice this. So we have two systems, system 1 and system 2. And here, the average Q waiting times are obtained across 7 replications, and both designs are simulated with common random numbers. So in the first replication, we use the common scenario, the same scenario. In the second replication, we use the same scenario, again, for both systems. Now, the sample mean and the sample variance across the replications are calculated, and also the sample variance across the replications are calculated. However, since the question tells me that it has used common random numbers, these two sample variances are not going to be useful for me at all. The important thing here is the difference row. So you take the difference of the both samples. For example, the difference between 5.60 and 5.94 is minus 0.34. So you always subtract the second one from the first one. You calculate the differences, and the differences average is minus 0.14, and the sample variance across these differences is 0.071. And as you can see, the 0.071 is neither the summation of these variances nor the difference. Okay? It is totally something different. Okay? Why? Because there is a correlation here. Due to the correlation, the difference has a different variance than the summation of the sample variances. Under a 95% confidence level, test if any system yields a significantly less expected waiting time in the queue, and we'll see about this. Now, we are just focusing on the difference row and the sample mean in the difference row and the sample variance in the difference row. My degrees of freedom parameter is number of replications minus 1, which is equal to 6. And my T quantile for 6 degrees of freedom is 2.45. If you check the T table here for 6 degrees of freedom and 0.025 quantile here. And the confidence interval that I built for the mean for the differences is the sample mean minus 0.14 plus minus 2.45, which is the T quantile, times the sample standard deviation, which is the square root of 0.071, divided by the square root of number of replications, which is square root of 7. And that confidence interval, my friends, is unfortunately covering the zero value. So the confidence interval built for the difference is including zero itself. So we should say that the result is inconclusive. There is not a significant difference between theta 1 and theta 2. Therefore, the comparison is inconclusive at this point. However, you know that if you increase the number of replications, you are going to get a better estimate for the sample mean for the difference and the sample variance for the difference. And as you increase the number of replications from 7 to, for example, 20 or 30, then you are going to get much more reliable results and with a conclusion. Increasing number of replications is going to create more reliable results. In fact, you can come up with a conclusion about which system is better. Maybe right now it seems that the first system is better, but maybe the second system is better actually. I mean, maybe you will be able to see that when you increase the number of replications. Now, there are some issues about the common random numbers here, my friends. First of all, the common random numbers method reduces the variance if the correlation between the results, the performance metrics, is positive. Now, how this is guaranteed? This is guaranteed if both the averages across replications under the first system design and the second system design are both increasing or both decreasing functions of the used random numbers. So if we have monotone functions that convert the random numbers into outputs, and you know, random variate generation using the inverse transformation technique is a monotone transformation. It is either an increasing function or decreasing function. I mean, in most of the simulations, the effects of the input variables are always going to be consistent in the output variables. So they are either going to be an increasing function or decreasing function, but there are some exceptions as well. For example, if the simulation function which transform the input variates is a nonlinear transformation or non-monotone transformation, sometimes we may observe that there may be negative correlation in the simulation outputs. If this correlation is negative, in that case, common random numbers methodology may even increase the variance and return less reliable results than the independent sampling. But usually, we do not see this in the discrete event system simulation. Now, how can you be sure that the correlation is going to be positive? Now, it says, for each specific purpose, dedicate a random number stream. Like when you are creating the entities with an arrival process, use a separate random number sequence, and that random number sequence is also going to be the same in the entity creation of the second system design. And when you are using another random number sequence for the service time generation, use that sequence for the service time generation of the second system design as well. And whenever you are making a chance decision, for example, a decide decision, again, you need to use a random number sequence, which is another random number sequence, which is the same for both systems, so on and so forth. So, for example, you can create a single simulation project with 2 create events and 2 process events and 2 different separate departure events. In parallel, you can watch the animations of both systems at the same time under a single project. Okay? So the animations of the 2 separate systems can be run at the same time in the same project. It is possible. So you can synchronize the both system simulations.